Okay, so first of all, a very brief introduction about Mars, just to get us all in context. And the first thing is that Mars, the name itself, was the name of the Roman god of war. And Mars is the fourth planet in the inner solar system. This is this one over here, and it is actually of the four terrestrial planets, rocky planets that we have, somehow similar to the Earth. This is the farthest one. And it is a bit red because of the ferric oxide in the surface. It is actually this red color that gave inspiration to the ancient Greeks and Romans to give the name of Mars as the god of war. Then very basic parameters here is that it has half of the diameter of Earth. We see here a comparison. It has a fourth of the surface and a tenth of the mass. So that means that if we stay on the surface of Mars, we would have a third of the weight. So I'm about 90 kilograms. I would be weighing 30 kilograms on there. The atmosphere on Mars is very small, very thin compared to that of the Earth. And the Martian day is very similar. It actually has more or less the same duration, about 1 hour more. Whereas the year is twice of that of the Earth. And has two little moons, Phobos and Deimos, that we will be seeing later. So now we start the story. This was just a brief context, but let's start the story from the beginning. What did the early humans see in the sky? So that's without technology, just by looking at the lights, the bright spots that they see on the sky. So the first thing they saw was that there are a lot of bright spots in there, mainly the stars, but there were many of them that did not follow the same movement. So they were moving from day to day, from season to season. And these were these five: Mercury, Venus, Saturn, Mars, and Jupiter. These were what they called the traveling stars. That's the traveler stars or wanderers. These were called then the planets. This is what planets actually mean. And they gave name to these 7 anomalies, but I actually only mentioned 5: Mercury, Venus, Saturn, Mars, and Jupiter. The other 2 planets, although they had separate names, they were actually the moon and the sun. These were the other 2 objects that were traveling in the sky without following the rules of the rest. So they were special. There was something weird going on with them. But they didn't know much more than that. The only thing they could see was the movement. So these gave actually drove the mythology. These are actually the reason why we have 7 days of the week, and the reason actually of the names of the weekdays. In particular, in English, it's moon for Monday and Saturday for Saturn, Sunday for Sun. But in Latin Roman languages, it's even more evident. So basically, in this era, without any technology, no telescopes, of course, no satellites, there was very limited knowledge, and the only thing they could do at the time was actually speculate, and then this drove to mythology and not real science. The real science will come later on. They could have done. They did know some things about the movement of the planets, but not much more. So that's why the mythology was boosted. But then, thanks to the technological advancements, the next step was the invention of the telescopes around the 1500s or early 1600s. The first one to actually use it for science was Galileo, to take this telescope and start looking up at the moon, at Venus, at Mars, and everything that he could find up in the sky. It's very well known, the findings of the moon, actually the phases of Venus. On Mars, he also looked at it, although he did not see anything interesting. His telescope was still very basic. But only a few years later, once the telescopes improved a little bit, another astronomer, Huygens, observed a dark spot in Mars. It's very, very faint, but he actually did these drawings at the time. And just by seeing this dark spot, he could already calculate the rotation of this object of Mars. He didn't know what it was. It could be a ball of fire, but he actually saw that it had a dark spot in there that was rotating. It had a duration very similar to the Earth. It actually calculated also the diameter of this object, which he calculated to be 60% of the Earth, which is quite amazing how he did that. And also he saw this little spot in here near the pole, which he already identified as a polar cap. So we went from a time where these objects were traveling the sky and were basically gods, no one knew what they could be, to in 1659, we get to a point where we actually are thinking in a completely new world already at these times. It was still very speculative, but it is completely changing the mindset at the time. And this was, again, driven by technology, driven by the new telescopes that were bringing more and more knowledge. So we went on and developing better and better telescopes until the end of the 19th century. And here we get one of the best images at the time by Schiaparelli, but the problem is that the technology was reaching its limits. And we could see some more features on Mars. We could see even better the polar caps, but the quality of the telescopes was still very, very bad. So then this limitation in technology started then again driving the speculation. So they could not really interpret these images, and they started seeing or trying to interpret what they call the optical aberrations of the telescope, these limitations of the technology. So the astronomers here, they started to see things that were not really there, and they started to hypothesize, speculate on what these channels could be. So they actually did these maps of the planet. So some of them are real features, but all of these channels here, they were fake. They were not real objects on the surface of Mars. But this was again limited by technology. The technology had reached its limits, and then the floor was open to speculations on what these channels could be. And it is amazing how these continued actually until the 50s. If you see some of the documentaries of space of the 50s or even early 60s, you could see that this was the concept that they had of Mars. It was a flat land of channels with water, probably built by Martian civilization. And this was present in all sides of society. This was very well known. The War of the Worlds by Orson Welles, 1938, but also many other documentaries of those times. So then we get to the space era. This was in 1957, the start of the era. It was the start of the space race between Russia and the United States. Russia was the first one on the 4th of October of 1957. They launched this little satellite called Sputnik that many of you may know. And it is really amazing how you see the date here. It was 1957. At this time, still, they did not know anything about the surface of Mars, about what was Venus made of, all the objects out there. There was some insight thanks to the spectroscopy, but still it was very, very light. So it was a major breakthrough once they actually managed to get out of the atmosphere. In 1957, it took them really, really short time to start sending things farther away. And this was the next step. You see, in 1960 already, only 3 years after Sputnik, they were already sending missions to Mars. First was the Russians until 1964 with the Americans. We see here all these first region here on the left. This is the core of the space race until 1975. And here, after 1975, with the Vikings, there was a stop. There was basically the end of the Cold War and the reduction of the missions. Only until the late 90s we see that the space race, or not the space race anymore, but the space missions were boosted again, not only United States and Russia, but now also with Japan. We also see here Europe coming up in the early 2000s. So there's a lot of information in this graph that was just showing how it works here on the left chronologically. But then on the right here, these circles mean, well, the first circle here was that the mission was a failure. So that the mission did not meet its objective, did not reach Mars, or did not leave the Earth, or something else. The next step is a flyby. A flyby meaning that it passed through Mars but did not stop there. This was actually the first successful mission to Mars. It was the Mariner 4. It took the first pictures of Mars. And then the next step, we had Mariner 6 and 7, also with flybys, taking picture. And the next step that happened in the early 70s was an orbiter to Mars. So actually managed to go to Mars and stay there for a while, taking images, taking data from the surface of the atmosphere. And this was again in 1971. But we see that the next step, which is a lander, is to actually touch the surface, has only been done 7 times. Well, we are missing a few in the late years. It has only been done 7 or 8 times now, and only by the Americans. So Europe has not yet been able to land on Mars. In Russia, well, did land on Mars, but it was not successful. It was only operated for a few minutes, so it was not really successful. And then also the rovers, it was only the Americans here. So a part of all the information that is given in this graph, the main point I want you to bring home is that it is very difficult to go to Mars. So about half of the missions that have been there actually failed. And while we are learning and we are getting more and more missions successful nowadays, it is still very, very challenging, especially to land in there. Only the Americans have been able to do it. So we get to our times nowadays. We saw before that in the early 2000s, we had a new armada of missions going to Mars, with Mars Express from ESA still operational, Odyssey, MRO, and the Opportunity and Spirit rovers from the Americans. Then another point to mention here is that the windows, what we call windows to get to Mars, actually happen every 2 years. So we are only able to launch spacecrafts or missions to Mars every 2 years. So we had here 2001, 2003, 5, 7, 2009, 11. Here it happened around December, January. So this is when Maven, the atmospheric mission by NASA, was launched. And we also have another partner there, the Indian mission, Mars Orbiter mission, and Curiosity. And then we got to the last ones in 2016. The last one by ESA was Trace Gas Orbiter, which we'll be mentioning later on. And the last one that landed there was in 2018, was InSight by NASA as well. And then we get to 2020, which is also a very crowded year, with missions going to Mars in this very moment. At the moment, they're traveling through space on the direction to Mars. And we have another very big and impressive rover by the Americans, Mars 2020. But we also have another 2 partners, which are China, which have an orbiter, a lander, and a rover, and the Arab Emirates, the HOPE mission that is also traveling to Mars. This is what we have at the moment in space, working and going to Mars. And then in 2022, we will have also the ExoMars 22 mission, which is a collaboration between ESA and Russia, we will mention later. And then we will be mentioning at the end a little bit about the Mars sample return and the other future missions or projects that may go to Mars. There's even some private initiatives that are still quite uncertain, but they may still make it in the next years, who knows? But we still have a long way before we can actually have astronauts in there. But we are working on that, but there's still a lot of technology we need to bring. The next step will be Mars sample return. Okay, so let's go back to the present, to Mars Express. Mars Express was and is still the first European mission to orbit another planet. It was actually the first mission of the called Rosetta family, which was Rosetta, Mars Express, and Venus Express, and it's still operational since 2003. And it has recently been extended until 2022. We're hoping to get it extended even further until 2025. Mars Express is in orbit around Mars since 2003, and it's looking at all of Mars system and as a whole. When we take a trip somewhere, we go to an island to visit some new place. We want to take pictures of everything and learn as much as possible of the place. And this is what we are doing with Mars Express. We're looking at Mars from the interior, measuring the gravity field and trying to understand how the composition, morphology of the interior, the subsurface, the surface, of course, geology, composition, mineralogy, the craters, volcanoes, mountains, everything. And then going up to the atmosphere and the ionosphere, trying to see how they interact and what is the composition and how the dynamics of the clouds and the dust works in the atmosphere. That we will see is very, very important. Not only that on the planet itself, but also the two moons, Phobos and Deimos. And so to go through this, I will let you this video. Okay, so I'll just go through some of the images here. We see these are real data, by the way. This is data taken from Mars Express itself. We can see valleys carved by rivers in the past. We can see the craters, and we can see some effects here of the dust falling from the craters. We see the water ice. Yes, there is water. We will see a lot about that. There is water on Mars, and it's a lot in the form of ice or glaciers, as we see here. There's also tectonic activity in there, and we see also the minerals in the surface. We will look at that. We have done many discoveries. One of them was the auroras on Mars. We are imaging the subsurface with a radar, so we can build 3D model of the ice of the polar caps. And we are looking at the atmosphere as a whole with radar. Also the Mars moons, those were Phobos in here. We can see also the craters and features in there, and Deimos, which is the farthest smaller moon. Not only that, but we are also using the spacecraft to support NASA missions, and also in collaboration with TGO, with ExoMars. We're doing a lot of science together. Okay, so let's move on to the next one. Okay, there you go. Okay, so this was a very brief video. Just to check, can you still listen to me, Michael? Anyone?
Yes. Amazing.
Yes. Yeah. Okay, I'm just checking. Okay, so what I will do now, this was a very brief and quick video of highlights of the mission, but what I prefer to do is drive you through some of the discoveries of the mission that have been occurring in the past year. So I will be going through a few topics. The main one, of course, is liquid water and potentially life. But I will also mention the methane mystery and the atmosphere. So these are things that we have learned in the past years, thanks again to this new technology, to the space missions, in particular Mars Express. And then I will go to the next ones in ExoMars. So why is liquid water important? The idea is that we want to know if there's life, and we know that life is very related to water. So this is why we are chasing the water and trying to find out where water is outside of the Earth. So let's think a bit about this issue of life, which is quite amazing. If we look at us here on the Earth anywhere, if I ask you now to look at your hand, actually, if you would do this experiment here with in a lab, you could actually see with a microscope that there are millions of microbes of organisms living on your hand at this very moment. Okay, so anywhere you look at the Earth, at your table, at your walls, everywhere, even your hand, there is millions of organisms. But when we look at Mars, at the moment, in one entire planet, there is not a single living organism. That is at the moment, it's amazing for me, at least. It is it's very impressive to think that there is more life in my hand that actually there's in one entire planet. Actually, at the moment, there's more life in there than anywhere in the solar system, or actually in the universe. And this, for me, this is very difficult to understand. There must be something out there, and we need to go and find it somehow. So if we look at the Earth, we have life everywhere, no matter where we go. We go to the deepest of the oceans, we go to the driest place, we go to the coldest place below the glaciers. We see microbes swimming there, even in the waters with very acidic, very salty, like this one. We find microbes everywhere. There's only one thing that is actually in common. The only thing that they need to live is water. This is liquid water is the key. This is the famous water bear or tardigrade. This is this famous animal that is it's called the immortal animal, because they live in all kinds of conditions, and you can actually boil them or bring them to space or dry them or do whatever you want with them. That the only thing they do is they just dry out, and as soon as you put a little bit of water on them, they will then start swimming again and leave. So it has actually been proven that these little bears can survive in space conditions, and actually they were brought to the moon recently by one of the recent missions. So, okay, this is just an example to understand that we see life everywhere, and everywhere we see it, it's connected to liquid water. And even in the dry places where there's no liquid water, the microorganisms will use either the salt or some other condensation process to find the liquid water and leave. So then we go to the concept of habitability zone in our solar system. Basically, we look at the inner planets here: Mercury, Venus, Earth, and Mars. There is this definition of habitability zone, and this is the limits where we go from having a place like Mars, what we could describe as a global fridge at the moment, with almost no atmosphere, to on the right neighbor, on Venus, we have a greenhouse oven. So there's somewhere an equilibrium between of course the input of power from the sun and the distance, where we can find the balance, so we can have actually liquid water on the surface and have a habitable place to live. And this is the limits we're trying to find out, because these are we will see now in a moment that actually these limits, they depend also on the conditions of the planet itself. So Venus is a hell at the moment. It's a greenhouse oven, but not only because of the distance of the sun, of course, it is closer to the sun, but the main reason it's the atmosphere. It's an atmosphere that actually broke the equilibrium of the planet and drove the temperature to go to really, really high temperatures. And on the other side, on Mars, it is very cold, but it could have hosted liquid water, and we will see in a moment some of the liquid water in the surface. But the reason there is no liquid water at the moment on Mars is actually the atmosphere. So it is not only this habitability zone, it's not only the distance to the sun, but the atmosphere is playing a key role. And this is why we have to study it. So I promise this is the only plot I will show in my presentation. I don't like showing plots in this kind of presentations, but this one is very important and to understand what is going on here. So the main scale I want you to look at is down here. This is temperature. Okay, the idea is that if we are on Earth, we can see that the water goes from solid state, that is from water ice, to liquid state. It just liquefies at 0 degrees. 0 degrees, of course, that is the definition of Celsius. So at 0 degrees goes from ice to liquid water, and at 100 degrees will go from liquid to vapor, water vapor. So this is what happens on Earth. The problem we have on Mars is that we are just below this limit here, about 600 pascals or 6 millibars. This limit below there, where the water goes directly from water ice to water vapor, and this is actually what we see on Mars. At the moment, we see ice in the polar caps, and we see vapor in the atmosphere, but we do not see water, liquid water, running through the valleys, although there was in the past. So the reason we don't see it at the moment, it's because of the atmosphere. If we add more pressure to the planet at the moment, we could actually be slightly higher in this curve. We could then move up here and then see some liquid water running in there. So it is not the temperature that is driving this process, or not only the temperature, but it is the pressure of the atmosphere. Okay, so we will see some more examples now. Okay, so we have to, this is a recent map of how Mars looks today. I want to give you just some basic ideas here of what we see, and we're going to try to reconstruct the history of Mars backwards from here. Okay, so the idea is the very basic thing that we see. There's two very different regions, and the northern hemisphere is very flat and low. Here, blue does not mean water, not yet. It means altitude. Although we always, on the maps of Mars, we tend to put the lower areas in blue, because we do think that there was an ocean in this area here. So this is in the north, it was flat and low, and in the south it is high, and also it is very, very rough. There are actually a lot of craters in here. We see, well, of course, these two gigantic craters, Argyre and Hellas, but also a lot of rugosity in all the area. This rugosity, it means that there were a lot of craters. This means that this area is very, very old compared to the north. So we have an old south and a young north. And then here on the left, we see an area which is also young compared to the south, but has these features here. These are the Tarsis volcanoes. This is Olympus Mons, the highest volcano in the solar system. So this is an area with a lot of volcanic activity. It was actually cleaned up the surface compared to the south. Okay, so this is just the basic idea, and even already at this level, from the very first let's say images from far away of Mars, we can already see some areas like here where we see some traces of what could be a river. Even if we look at this without knowing much about geology, you could recognize some features that you may think, okay, well, this looks like there was a lake in here and the water was going down through these lakes and up to an ocean in here. So this can already be seen at this scale. And this is actually possible. We're still trying to understand what happened, but we need to go back a little bit more. So we try to understand what happened because we see Mars as it is today. It's just a gigantic desert at the moment. But we maybe, as you saw, maybe there was some water near the north, or actually maybe there was water in all this ocean in the north, and the craters and the valleys were filled up with water, or maybe the water was all covering the planet everywhere, not only there, but actually everywhere else, and different conditions. And the question was, when any of these scenarios happened, when there was liquid water, we know that to have liquid water, we also needed an atmosphere. So then the conditions would be very similar to what Earth is today, or was when the life emerged. So in these conditions, was there life at the time, or was it possible for life to live there? This is what we're trying to find out. Okay, so we're going to look at this history of Mars through various aspects, various topics. The first one is analysis of the geology. We do this with cameras typically. And as I showed you before, some of these areas, we see that there were rivers. This was clearly liquid water running on the surface. And this is the edge of the of the river, when we would reach some sort of lake or sea or ocean. And we also see glaciers. This is not liquid water, but actually ice. We see glaciers of ice flowing still today on Mars. But then, as I told you before, you could look at the craters and look at how old these regions are. And we see, we can actually measure the number of craters, and we can estimate the age of the area. And we see that the fluvial areas, all of them are very old. I can put here 100 million years old, but typically they're even much older, like 3,000 million years or 3 billion years ago. Whereas the glacial structures are actually much more recent. So we see already there an indication that the liquid water was there far away in the past, but not in the present again. We now look at the mineralogy. That means the chemistry of the rocks. We can look at this with the spectrometers. We can see basically the colors of this rock and find out which mineral it is. We see, for example, here, this is the ferric oxide. We see that the upper region is mainly dominated by dust, by ferric dust, basically. But if we look at some minerals, what are called the aqueous minerals, or the hydrated minerals, these are minerals that were found that are, formed in the presence of water. So it's not minerals that are wet just a few minutes or hours or decades. These are minerals formed under a lake or an ocean for thousands of years. So, and when we look at the rivers here, the images before, we see a channel of a river here going into a larger lake or ocean. But actually, we don't find the minerals in this region, which is odd. Well, probably because they are covered by sediments. But we actually find the minerals in the older region, in the region that was before that river. So actually, if we look at the map, we find we were speculating before that the rivers could go from these areas to the north, to the ocean north. Instead of that, we find the hydrated minerals in the older regions. So that would mean that the ocean was not in the north, but would maybe be in the whole of the planet before. So these are different theories, different ideas that we're still trying to find out if the ocean was again in the northern area or in the globally in the planet. Actually, this is more or less how it could look like now. If we look at the present, again, it's a giant desert. But then we see that there was some, sorry, let's go back. We see that there was a region where potentially there was an ocean in the north, but maybe it did not stay there for too long, not enough to make these minerals, but farther away in the past, there was a global ocean that covered the planet just after it was formed. And it is interesting to see that we compare Mars with Earth this time, around 3.5 to 4 billion years. This is more or less the time where life was formed on Earth. So at the time life formed on Earth, we know that Mars had similar conditions to what we had on the Earth. So was life formed on Earth and not on Mars? Was it formed in both? This is a question that we have to answer. Okay, so we see that there was a lot of water in the past, liquid water, rivers, lakes, probably oceans as well. But where is the water now? At the moment, we just see this desert. We see here some images of the sand dunes. Where is the water? We don't see any water in the surface at the moment. But actually, we do see water in the polar caps. We are measuring it. We have this radar that we are able to build a 3D model of the polar cap. So we are actually able to see how much water is trapped in the polar caps at the moment. Not only that, but with this radar, we have been able to identify liquid water also. We know at the moment, there was a discovery in 2018 that in some regions in the South Pole, so down here, we did this radargram, it's called. You can imagine it as an echography, let's say, and a radar image going down. We could find 1.5 kilometers below the surface, there was this water lake. So not only water ice, all of these areas water ice, but also liquid water. This was the first time this was discovered. And this was even confirmed just a month ago, or actually 3 weeks ago, that we could see that not only this big lake, this is the lake that was found here in the South Pole, but actually there is a network of lakes around this area. So we know there's liquid water down there. The problem is, how can this liquid water be still there? The conditions that it has to have, probably it needs a lot of salt, and some of the models predict that there may be some heat coming from the core of the planet, so there might be some geological activity down there. Still, we still need to find out. But the interesting idea is that these liquid water lakes may still have some life in there, because we know that in some of the deep lakes on the Earth, below the Antarctica and the North Pole, we have living organisms even at this great depth. And without light, there's, as I mentioned before, life finds its way to survive. First to stay there and then survive. So also water is in the atmosphere, and we can even see it. These are actually images by the cameras and the spectrums. So we see this is a water cloud that is forming regularly in one of the volcanoes. This is Arsia Mons. And we see this water cloud that forms and it extends more than 1,000 kilometers. But not only this is condensation in the clouds, but we actually have water vapor all around the atmosphere, and we see that with the spectrometers. Okay, this is just a summary, by the way, that I forgot to mention about the comparison of the atmospheres of Mars and Earth. We know that on Earth, most of the atmosphere, 80%, is nitrogen, and we have about 20% of oxygen in there. This is, and then we only have these small parts here, about 1%, which are all of the other gases, argon, carbon dioxide, and especially this one here, water vapor. There's very little quantity of water vapor on Earth, but still enough, of course, to keep us living and breathing. On the other side, on Mars, we have most of it, 96%, it's carbon dioxide, then 2% of nitrogen and argon. And the water vapor and even the oxygen are what we call trace gases. These are, there is water vapor, oxygen, ozone, a lot of other things. But we still don't know exactly how the atmosphere was formed, and how it works. We know on Earth that although carbon dioxide, for example, or water vapor or ozone are very, very small in quantity, we know that they are a key player in the climate of the Earth. The same happens with Mars. We need to understand not only how the carbon dioxide works, we know there's a lot of it, but we need to understand all of the rest of the gases to understand how the atmosphere works. Because as we said before, it was the atmosphere that probably drove the existence of water lakes and water rivers and liquid water in general in the surface. So there is some water in the atmosphere, but what happens then? We also look at the outside of Mars, the magnetosphere of the planet, and how the atmosphere interacts with the solar wind from the sun. And we actually see that the water is escaping from the ionosphere. So we see that these water vapor molecules, H2O, in the atmosphere transforms into atoms or ions of oxygen and hydrogen. And we can actually measure them with a plasma detector flying around here. We can see that these hydrogen and oxygen atoms are actually running away of the planet. So this is one of the theories, that the water that was there on Mars escaped. We know that there's still some in the atmosphere. We know that there's quite a lot still in the ice in the poles, but many of the molecules of water could have escaped in the history through the solar wind. And this process is, well, first because Mars does not have a magnetic field like the one of Earth, but not only that, but it's also because sometimes the water gets very, very high in the atmosphere of Mars, whereas in the Earth we have this cycle that water goes up in the atmosphere, and then at a certain point, which is a limit, condenses in clouds and then stays down. But sometimes on Mars, we have measured actually that, especially during the dust storms, the dust brings the water up in the atmosphere. So I will show also more later. This is something we are investigating, and this is why it is very important to study the dust storm. This is another image that was taken in 2018, where we see the surface here on the left, and we see how the dust storm is raising, is getting very, very quickly here on the right side. And we are also measuring here other local dust storms. Here we can see also another cloud of dust flying very close to the polar cap. So in general, we need to monitor the climate variability, and for that we have models. We have a global climate model to understand how the atmosphere works, and this model is built using data from the planet. And in Mars Express we have 17 years of atmospheric database of all different molecules, oxygen, water vapor, ozone, dust, temperatures, everything. This is what we're doing year after year. monitoring how the atmosphere works. And then we put that into a global climate model to understand how the atmosphere is working on Mars. Because again, it is the atmosphere that is driving the climate of Mars, that is probably driving the existence of liquid water. So we go then to the next topic, the atmosphere, which is methane. Methane was listed before as one of these trace gases. This is something that is very, very small at the moment in the atmosphere, but it's very, very weird. And there's a whole mystery and controversy about methane currently in the past years, because methane should not be there. Methane, well, is an atom of carbon and 4 hydrogens. And it's a molecule that if you put in the atmosphere of Mars, it should get destroyed within 300 years. So even if someone or something like a comet or an asteroid or whatever brought methane onto the atmosphere, it would disappear very, very quickly in a few hundred years by different processes. The problem, the controversy came in 2004 when 3 different groups around the world detected methane. One of them was the team by Vittorio Formisano on Mars Express, and found this little band over here, which was very controversial, because they claimed that get this thing out. Because they found an amount of methane that was completely unexpected. Again, the models predict that there should be 0 methane in there, and different proposed presence of methane in there at different levels. But why is all this mess about methane, all controversy? It's just a gas. The problem of methane is that the existence of methane has great geological or biological implications. In particular, if we look at methane on Earth, we have a lot of methane on Earth compared to Mars, but this is 80%, around 70 to 80% caused by living microbes, basically. So one of the famous ones, for example, is the microbes that live in the stomachs of the cows. So the cows, the meat industry on the Earth actually is a methane producer. So these microbes live and decompose in the stomachs, decompose the grass, basically. The food, and then they emit here the methane to the atmosphere. So these microbes are a known source of methane. The other possible origin is geology. The other origin of methane on Earth is the geology. In some geological processes, can produce methane, although they're very complex to understand. But basically, some thermal subsurface processes can produce this methane if they have water next to it. So in any case, as we know it on Earth, we have methane produced by all geology with liquid water. But these 3 things, any of these 3 things would be a major discovery on Mars, because on Mars, at the moment, we don't know if there is life. We don't know if there is any geological activity, meaning active volcanoes or active subsurface geology, or liquid water. Liquid water, we now know there are these liquid lakes very deep in the surface, but we need to understand how these processes work. So, these are some of the theories that could explain the origin of methane. There was that maybe these deep lakes, there's some processes, or either volcanic or hydrothermal processes, or eventually some biological activity that would produce this gas and bring it up through the cracks in the atmosphere. Okay, the story was a shock in 2004, but then we continued investigating. There were a lot of measurements at the time by the Americans, by us in Europe, by our colleagues in Italy, but they were producing maps of methane, but they were very confused because they were producing very different results. And again, the modelers, the people that know theory, how the atmosphere should work, they were still are still very strong defending that it cannot be explained. So we had this very hot debate in this meeting in Rome in 2009. Then we had we needed more data, so we brought new instruments to the surface, and there was Curiosity in 2013. And the first measurement they did not find any methane. So, and we saw, okay, this is now this thing. Then they found no methane in 2013, so we thought it was more clear, but then again, more controversy the year after they saw that the methane was there, but actually is even more clear is that we see some peaks in there, and we also see a background level of methane that comes and goes seasonally. This was very weird, and it's not explained. So not only now we need a way to create the methane, so we need either bacteria or some hydrothermal activity, but now we need something to eat methane or to destruct the methane, because by photolysis or by absorption, it does not disappear so quickly. So we need a way to explain this, or to transport this methane around. This is not. This was controversial, but it was also confirmed again by Mars Express 2019. So we actually observed one of these peaks seen by Curiosity. We saw it with Mars Express as well. We even identified the region where this could come from. This is where MSL is sitting, and we identified that this region is of potential interest because the wind could have transported this methane from these regions to there. So then we now need to see what is going on in these regions. Okay, this is just a model again to illustrate that if we produced some methane in here on the surface, we would see that only after a few days the methane would actually spread all around the atmosphere. So it is very difficult to explain how the methane would be seen after a few days. So it is very complicated to understand, and no one really understands it further. So the only thing we agreed was that we needed more data. So with the current instruments, even with not only Mars Express, but with MSL, we needed more data, we needed more instruments. Okay, and this is where we decided, okay, let's send another mission. And this is the next step, that is the ExoMars program. And the first mission of this program is the trace gas orbit. So we actually sent a satellite specifically to look at the methane, at the trace gases, and try to find where they are, if they actually are there, to try to prove it, and if they are, where are they coming from? And then the next step of the mission is still for the future. This is the rover and surface platform for 2022. One second. Okay, so ExoMars 2016, this was the first mission of the ExoMars program, and it had a technological objective, which was to test the entry, descent, and landing concept. This was Schiaparelli. This was just a test to try and see if the systems were working properly. And well, we still didn't make it to the surface, but we learned a lot on how the thermal shield, the parachutes, and the attitude control, a lot of details, all the subsystems worked. So we gained a lot of useful information for the next test. Sorry, for the next landing. That's in 2020. And the science objectives, that's what matters for us at the moment, is this mission, the Trace Gas Orbiter, this satellite here that has 4 instruments with the main goal to look at the trace gases and the sources of these gases, if they are and where are they coming from, activity, volcanic activity, the links to life, and understand the chemistry of these gases. And then has 2 other instruments, a camera and a neutron spectrometer, trying to look at the surface and the ice content. By the way, it also serves as a communication platform for ESA and NASA rovers. Okay, so this is Trace Gas Orbiter. This is what I like to call the Sunset Hunter. So how do we look at the trace gases? The way of looking at these trace gases is looking at how these gases behave with the sun, or how they absorb the light of the sun. The way we do it is we actually observe the sun directly, and then we'll see how the sun goes behind the planet. And with that, like we are looking at the sunset on Earth, or the sunrise, they look at both sunset and sunrise, we can see how the color of the signal changes. Wait for the bells 1 second.
Alex, this tells you that your time is up.
But how much time do I have?
The hour is over.
But we have one more, right?
Sorry?
I have 1 more hour, right?
No.
No. Okay, that is great. Okay, that is a very good surprise. Okay, so should I finish with the video then of ExoMars, and then that will conclude?
Please, yes.
Okay, let me just show the video at the end, and just so that we can. Okay, so let's just let you this video that shows all the program ExoMars. Do I have 1 minute to describe it, Michael?
Yes.
Okay. So this was the first launch in 2016. It was done in March 2016, and we see the spacecraft separating from the final stage of the rocket and traveling to Mars. It actually had, as I said before, the Schiaparelli lander that was released onto Mars, although it did not make it to the surface, but we used it to test the technology of the landing. And we have been observing the atmosphere. That is the release of the lander, by the way. And we have been observing the planet and the atmosphere since 2016 now. Then it goes the next step in 2022. It did say 2018 there was the original proposal, but because of various reasons we had to delay it. So we had the rover and surface platform that will be launched in 2022, arriving in 2023. So this is a very complex program because it is in a collaboration with Russia, and we have a Russian launcher and then a European carrier. And then that is the landing platform that is going down there. Of course, the spacecrafts, both Mars Express and ExoMars, will still be looking at that. Okay, that is again. So we will have two parachutes going down. Damn it. Sorry for that. Okay, here we see the Russian landing platform, which will then bring the rover down to the surface. And the surface platform will also do science and understand how the environment looks in the atmosphere. And this is the rover. Okay, I will go a bit faster now just to go there. This is how the rover will go down of the platform. And the main thing here I want to show is just the drill that will go and collect samples of the subsurface and measure them in the lab. Okay, I'll stop here and not sure if there's any questions.
Yes, can you see the chat, or shall I read it into you?
If you can mention it to me, I need to see how.
So there's a question. Water in Mars disappeared due to the lack of magnetic field, and the dust storms bring water vapor to the upper atmosphere, as I understood. Wasn't the dust generated after water disappeared?
Well, the water was the dust was probably there also before. It's now that we see it more clearly. Of course, if it had been the water had been there, it would have probably trapped the water in this ocean. But I mean, in general, the answer is that we don't know, and this is why we still need to find out. We still don't know how the dust storms work nowadays. We have observed these features, for example, that they heat up the whole planet and they disturb the climate every 2 years or every Martian year. But we don't know how they worked in the past. We don't even know how they work in the present, so we need to build backwards again.
Yeah, and then there was another question saying, so the cladrats melt and spread the methane in summer.
That is one of the theories that actually could explain the creation and destruction of the methane. This is there is a group in Madrid in the Centro de Astrobiología that is working on this. They are experts in these topics. And this is indeed one of the possibilities that could explain the methane. But okay, I did not get to that. But with TGO, with the Trace Gas Orbiter, at the moment we have not yet observed any methane the past 2 years. After 2 or 3 years, 2 years observing Mars, they have not yet seen a single molecule of methane.